Dynamic networks. Roughly speaking, they are networks which change with time. They always existed. Social networks, friendship relations. But we did not have any theory about them, and we realized lately that we should.
Based in the Department of Computer Science at the University of Liverpool, Paul Spirakis and Orthon Mikhail have been researching the challenges we face computing in highly dynamic environments and discussing the future of the field.
The most interesting aspect about dynamic networks is the fact that we know that we do not know many things.
The most vital thing is to develop a theory about them. In order for us to be able to design them, to predict what's going to happen, and if we can, to control them.
So we need new approaches, we need new measures, new metrics, and to develop radically new algorithmic solutions and maybe change our way of thinking and arguing about this family of systems.
If we go to dynamic networks that are formed between molecules, then these things cannot really remember a lot of information. One could say that it's like simple automata interacting with each other. And we want to know what can be stably computed by those dynamic interactions in this simple model. Unfortunately, it has been found out that not many things can be computed there. Now we found out that the more memory we add, the more they can compute basically. And in fact, if you add a lot of memory to each device, they can become as a whole as powerful as a Turing machine.
When we continued working on this model, we found out that there is also a very reasonable way to draw connections with real systems, like for example DNA self-assembly or areas like chemical reaction networks. So it is like studying the same systems from different perspectives, because even the traditional population protocol model can in some sense and under some assumptions be shown to be formally equivalent to some chemical reaction systems.
And now is an interesting twist. We found out that we can program these little devices with very simple programs. So they, when stabilized, they create very beautiful and unexpected networks. And in fact, the beauty of the fact is that you put a little program in each of them, a program which speaks about interactions. And then at the end, when the system stabilizes, you get a beautiful network like a global star or something that you wanted to do from the beginning. So this is the theory of network constructors.
One very important notion for dealing with dynamic networks is the notion of causal influence.
To illustrate causal influence, let's imagine you have some information. At some point you tell that information to a sibling. They might tell their friends that information tomorrow, who might tell their spouse a week from now. That information is propagating through time. Once the information has reached a desired point, you could ascertain that the process has stopped. From this information, you begin to be able to draw conclusions such as the size of the system, electing a leader in the system, and so on.
The next step, classifying the dynamic networks from the simplest to the more complicated. What we have left out up to now, we left out artificial intelligence. So I think the next step, I think it is necessary to add local AI capabilities to the nodes, to the entities of a dynamic network, and to see what the global thing can actually do.
My feeling is that we are going to see in the future very intense efforts towards studying highly dynamic problems and problems that are naturally motivated by existing highly dynamic networks. This is one important implication of this line of research, showing that by exploiting information and computing principles and techniques, we can gain a better understanding of the natural world.
To learn more about Mikhail and Spirakis' work on the theory of dynamic networks, read their review article in 2018's February issue of Communications of the ACM.